Now look at the next type of isomerism, which is called stereoisomerism. As I told you, stereoisomerism is of two types. One is optical and the other is geometrical. We'll first look at optical isomerism. First thing is that the optical isomerism means that if I pass light through that organic compound, the light changes its direction. The compound does not change. Compound remains the same, only light changes its direction. So what we do is, first take an ordinary light which is moving in all directions. It is passed through a Nicol prism. When it passes through this prism, it becomes in one direction. When light becomes in one direction, it is known as plane polarized light. So this plane polarized light will be passed through my compound, and the compound will change the direction of this light. That is, the light will start moving either in clockwise direction or in anti-clockwise direction. When the light moves in two different directions, then we call it that the compound is optically active. That is why it has changed the direction of light either in clockwise direction or in anti-clockwise direction. Now, important thing is that those compounds will show optical activity, only those compounds which have these three conditions. Now, what are the conditions? The first condition says that the compound must have an asymmetric carbon atom. Asymmetric carbon atom means that on the carbon atom there are four groups which are different. If the four groups are different, we will show it with a star, like in this compound here in lactic acid. The center carbon atom, which I have shown with a red star, contains four different groups: OH, H, COOH and CH3. So four different groups are present and so this carbon atom will be known as asymmetric carbon atom. If the compound contains asymmetric carbon atom, we will see that this compound can show optical activity. Number two, even if the asymmetric carbon atom is present, it should not contain any plane of symmetry. Plane of symmetry means, supposing I have a square, I can divide it equally into two parts. So there is a plane of symmetry. So such things are called symmetrical. Compound which does not contain plane of symmetry, that should be another condition. The mirror image is not superimposable on each other. See, in that compound, COOH, CHOH, CH3, if I make a mirror image of that, I've made a mirror in between. If I make a mirror image of that compound, this compound is not superimposable on the other compound. See how it is not superimposable. This was the asymmetric carbon atom. If I lift this up and put on this is called superimposable. I mean, I am imposing this on this. So COH will come on COH, but H will come on OH, OH will come on H, and CH3 will come on CH3. That means the entire compound cannot be fitted on the other compound. So mirror image is not superimposable on each other. Like if I write R and I want to find out its mirror image, it's going to come something like this. So this cannot be put on this. So which means it is not superimposable. So you've seen on an ambulance how the ambulance is written, because if you are going to see from your own mirror in the car, you will see it in opposite direction. That is why sometimes it is written in a different way, so that on your mirror it is in the right way. So that's what it is. So the third requirement was mirror image is not superimposable on each other. If these three conditions are present, then we will say that this compound can show optical activity. So now this compound is optically active because it has an asymmetric carbon atom, and the mirror images of this compound are not superimposable on each other. So both all the requirements are present here. So I'll say structure 1 and structure 2 are optically active. Conventionally, we draw an arrow from H2OH and from on this side again H2OH. So it is showing me in clockwise direction. This is showing me in anti-clockwise direction. So we will say compound 1 rotates the plane polarized light towards the right or clockwise direction. So it is called D-lactic acid. D-lactic acid actually means dextrorotatory. And similarly, the other one is moving it on the other side, on the left, which is called anti-clockwise direction, is also called levorotatory. So, for lactic acid, we will say there are two isomers possible, 1 and 2. They are both optically active, and one will rotate the plane polarized light towards the right, and the other will change the direction of the light towards the left. Let us take another example, which is tartaric acid. Now for tartaric acid, molecular formula is C4H6O4, and if I draw the structure of that, it will come as 2COOH group and CHOH. Now this compound could have been drawn in 3 different ways. I can write in a single bond compound, I hope you understand that H and OH, all the groups attached on it can be put on any side. So this is what we can do. I can write down COH, HOH, COH, H and COH, or I could have turned it OH and H and OH, or I could have written both H on same sides and OH on same sides. So we could draw 3 different structures for tartaric acid. Now see, in all of them, there are asymmetric carbon atoms. That is, this carbon atom contains 1, 2, 3 groups, and consider this as the 4th group. So all four groups are different. This is asymmetric. Similarly, this carbon atom, 1, 2, 3 groups, and this group. So 2 asymmetric carbon atoms. So they contain asymmetric carbon atoms, all of them. So even this contains asymmetric, and all of them. So that means all 3 structures contain asymmetric carbon atoms. As I told you earlier, we will draw from H2OH. So this is clockwise, so it is called D-tartaric acid. Similarly here, H2OH and H2OH is anti-clockwise, so this is L-tartaric acid. And both of them are optically active. Now look at the third structure. This third structure, so let me come back to this, sorry. This structure has asymmetric carbon atom. If I want to put this structure on this is not superimposable, because if I put it on it, COH will come on each other, but H and OH will come on H. Similarly here, OH and H and OH. That means I cannot put exactly on it. So it is not superimposable. So both the criterias are completed here. Asymmetric carbon atom and the mirror image is not superimposable. That is why both these are optically active. The third one contains 2 asymmetric carbon atoms, but there is a plane of symmetry here. If I fold the compound, COOH will come on this, OH will come on this, H will come on this, which means that this compound is not optically active. And now how it is becoming optically inactive? Because if I am drawing from H2OH here, clockwise direction. If I move from here H2OH, it is anti-clockwise direction. So there is internal compensation. This is called internal compensation. That the molecule on its own upper part is compensating the lower part, and so it becomes optically inactive. So there are 3 structures which you can draw for tartaric acid. Out of them, 2 are optically active. The third one is not optically active. Now there are terms, enantiomers. So 1 and 2. structures 1 and 2 are called enantiomers, and enantiomers means that those optically active structures which are superimposable on each other, and they are mirror images of each other. So these two are mirror images of each other but not superimposable on each other. They are called enantiomers. If I compare 1 and 3, 1 and 3 are neither mirror images. I cannot say this is a mirror image of this one. So these two are not mirror images of each other. They are not also superimposable on each other. So they are called distereoisomers. Distereo means they have no relationship with each other. They are stereoisomers, but they are not related to each other. Same is with this and this. Both of them are not mirror images of each other. They are not superimposable on each other. So they are called distereoisomers. The third term I have written is a racemic mixture. A racemic mixture is a mixture. If I take 1 and 2 together, equal amount of A1 and 2, the mixture will again become optically inactive because this is moving clockwise, this is moving anti-clockwise. So they are again going to compensate each other, which is called external compensation. So again, racemic mixture will become optically inactive, and the reason will be that these two are from outside. I have taken equal amount of both of them, and that is why they become optically inactive. Individually, they are optically active, but otherwise they will become optically inactive.